Okay, so I start from 2.5 vector. The mathematical definition of vectors as a directed line segment with their starting point fixed at the origin enables us to express any vector v in a chosen coordinate system as v equal VIEI, where VI are the components of the vector in that system. In other system with unit vector E prime, we will have v equal vi prime ei prime. From our examination of the coordinate transformation, it is clear that two sets of components are related in the form vi prime equal qij vj. The dot product, inner product or scalar product of two vectors u and v is defined as u dot v equal ui ei dot vj ej equal ui vj ei dot ej ui vj delta ij ui vi. The cross product, vector product of these vectors is defined as u cross v is uiei cross vj ej equal ui vj ei cross ej equal ui vj epsilon ijk ek. In physics and engineering, there are many 3 times 1 arrays that transform from one coordinate system to another according to the transformation rule of equation 258. We call them vectors. Examples include position vectors, velocities, forces relative to their point of application, and gradients of scalar functions. That brings us to scalars. I don't know what this sentence here. That bring us scalars. What brings us scalars? These are quantities with no associated directions. Okay. I think this is more like this. Now we talk about Now we talk about scalars. These are quantities. Scalars are quantities with no associated directions. Examples include temperature, hydrostatic pressure, and density of matter. A scalar function psi can be written as psi equals psi of x1, x2, x3 in a different coordinate system using xi equals qij x j prime. We obtain psi x1 to 3 is psi qj1 xj prime qj2 blah blah blah, which shows that the functional forms of psi and psi prime are different. The numerical value of the function at a point obtained from psi x1 prime x2 prime x3 prime or psi x1 x2 x3 will be the same. I think there has to be prime here. The numerical value of the function at a given point obtained from psi prime or psi will be the same. When we examine the transformation of the derivatives of a scalar function, we use the chain rule for differentiation to get partial psi prime partial x prime equal partial psi partial x times partial x prime. From equation 262, partial xj partial x prime I equal qij. Thus, partial psi prime partial x prime equal partial psi partial x times qij. So the array formed by the three derivatives of psi obeys the transformation rule for a vector. We define gradient vector as gradient psi is like this. We can also introduce a vector operator, nabla. We call this nabla. In Japanese, nabla. Nabla, ei, psi I, partial I, where partial I is partial x. In the x prime system, we could use partial prime I equal partial x prime I. To simplify our label, we can express functions of a set of independent variables that belongs to an ambiguous family by using the condensed form. That belongs to an ambiguous family. Anyway, it's a little bit strange expression. Tensors. In 3D space, The 9 quantities T, I, J are called the component of a tensor T of rank 2 if they obey the transformation rule. Tij prime is Qim, Qji, Qjm, and Tmn. When the two coordinate systems are related by the rotation. Xi prime, Qij, Xj. The number of indices shows the rank of a tensor. We call T a second rank tensor. In 3 dimensions, a second rank tensor has 3 square components, and in 2 dimensions, it has 2 to the power 2 components. We can introduce a tensor of rank R in 3 dimensions with 3 to the power R components. T, I1, I2, Ij, Ir. The transformation rule for these components will have R number of Q's in the form T prime I1, I2, Ir equal Q I1, J1, Q I2, J2, Q IR, JR, T J1, J2, JR. From a heuristic definition of vectors as directed line segments in space, it is clear that these are independent of the coordinate system. However, to define the components of a vector, we need a frame of reference. What is this? What are these? It's very strange. What are independent of? What are independent of the coordinate system? However, to define the components of vector, we need a frame of reference. If we know the representation of a vector in one coordinate system, we can use the transformation rule to find them in any other system. Similarly, tensor T is an absolute quantity, and its component representation depends on the coordinate system, Again, when we know its components in one system, the use of the transformation rule to obtain them in another coordinate system. We use them. So, what is it? The transformation rule for these components will have R number of Q's. From a heuristic definition of vector as a directed line segment in space, it is clear that